Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge. So the problem is capacity to ship packages within D days. And so what this problem says is we get sort of a conveyor belt that has packages that we need to ship from one port to another within a number of days, right? And so the ith package has a weight that we get in the input, in the array of weights. And we load these packages into a ship. And so a ship has a capacity. And so we may not load more weight than the maximum, than the capacity of the ship, right? And what we want to return is the least capacity possible for the ship so that we can ship all the packages within that number of days that we get as input. So basically, how many trips does the ship need? So basically, what's the capacity we need for the ship to be able to move all the packages in X days? And basically, X is the number here, okay? So if you take a look at the first example here with days equal to 5, well, the minimum which will turn out to be the minimum is 15. And so that would be basically in the first trip, taking 1 to 5, right here. So that would be 6 for 15, right? And then in the second trip, taking 6 and 7, that would be roughly 13. And then after that, taking just 8, and then after that taking 9, after that taking 10, and that would be 1, 2, 3, 4, 5 days, right? So that's roughly the idea here, and that's the minimum. Now, in terms of the constraint, you can see here we have the weights size. The size of the array is up to 10 to the power of 4. So this rolls out anything that is O of n squared with n being the length of the weights, right? So we can't do something that is O of n squared. But we should be able to do something that is O of n log n. That should work fine. We should be able to do something that is O of n and then log of the value of the weight, right? Because any term that will be a function of the maximum value of the weights, that should be doable, right? Because it's just 500. So that's roughly a couple of things we can come up with from the constraint. Now let's see how we can solve the problem. Okay, so how do we solve this? So I think the main point here is to think about, so the problem says that we have some constraint, right? So we have some constraint, right? And then we want to minimize some value while respecting that constraint, right? And so basically what this is that we have a capacity of X that we are looking to minimize, right? But with this capacity, we want to be able to ship all packages, right, within a number of days. Let's call them D days, right? And we want to minimize this value while respecting this condition. And so this is sort of, we are looking for an optimal point with some constraint. And in most cases, this can be solved with binary search, right? So that's something to think about. The other hint that tells us that it's solvable with binary search is that the time limit or the constraint that we have on the problem are such that, for example, the length of the weights, right, is up to 10 to the power of 4, right? So this tells you if we consider the length of the weight to be n, we can't do O of n squared because that would be 10 to the power of 8. So that's not a right solution. But anything that is O of n log n should be fairly good, right? The other thing we have is that the value of the weights themselves, right, is up to 500, right? So something also that is a function of this 500 would be good, right? And so already with this, we know, okay, if we do binary search because the weights are already in an order that we have to respect, right? Because they are in a conveyor belt. So this order, if they weren't sorted like we had 6, 2, 3, 1, we still have to respect this order because they are in conveyor belt. Each one of them is after the other. So we can't change the order. So no sorting will help, right? But if we do binary search, we should be able to, either this is in terms of n, or even if it's in terms of the values of the weights, it should be largely good, right? And so that's also another hint of using binary search. I'm trying to just give you like what indices you can use in the future, what like hints you can use in the future to figure out that you can solve it with binary search, right? And so the main point here is that binary search people usually associate it with just searching in an array, in a sorted array, but that's not always the case, right? You can there is a version of binary search called discrete binary search. It has other names, but the idea is that instead of, it doesn't just apply to an array, it applies to any function that you can find, such that that function is monotonic. We'll define what monotonic means. And if you are looking for either the minimum value or a maximum value, then you can find it with binary search, as long as you prove to yourself that it's monotonic, right? And so what do we mean by monotonic? Monotonic basically means that once that function has some Boolean value, it stays at that value. So basically it means that it has this pattern. First it's false, then it becomes true, and when it becomes true, it will keep being true. That's the monotonic part. And in some cases, you might want to define it as first the values are true, and then once it becomes false, it stays false. And what you will be looking for in these cases, the answer you will be looking for to minimize or maximize something would be either the first false, the last false, or the first true, or the last true or the first false, right? So if you can write your function in one of these two ways, and what you are looking for is one of these, you can use binary search. And there is a template code that we can use, and that's what we will use here. In most cases, your function would be something like this, right? And then from there, you could just find whether you want the last false or the first true, and use binary search. Okay, so now that's just the idea of using binary search. Now, if we apply it to this problem here, we need to find our function. What function can we find? Can we use that will be monotonic? Basically, here the values false, false, true, true. Let's say if x becomes true, we need anything bigger or equal to x to continue being true, right? So what can we do? Well, we know that if you have a ship, right, capacity, right, x can take all packages in D days, then if you increase the capacity, you will definitely be able to do it in D days. You may be able to even do it in less, but with D days, you will largely be able to do that. And so this basically means that if you have a capacity like y bigger or equal to x, you will be able to ship within D days, right? And so basically if we make this our function, if we make f of x being whether it's possible, right, to ship all packages in D days, right, in less than or equal to D days, right, then if we use this as our function, then let's say maybe with the value of just capacity of 1, let's say in this case capacity of just value 1, it's false. We can't, because we can't take this 2. And then with capacity of just 2, we still can't. It's still false because we can't take this 3 value here. With a capacity of 4, let's say with a capacity let's keep going here. Let's say with capacity of 3, we still can't, because we can't take this one. With capacity of 4, we still can't, right? So with capacity of 4, we still can't. With capacity of 5, we can, right? Because let's check if we can with 3 days. So for 5, we can take 1 and 2 in the first day. We can take 3 only in the second day, right? We can take 4, and then we can take 5. So 1, 2, 3, 4. So 4 days with 5. So 5 is false. What about 6? So with 6, we should be able, let's say 6 here. Well, with 6, we should be able to say, take these 2, So that's day 1. We should be able to do this one, and day 1, and day 2, and day 3. So we should be able to do it with 3 days. And so with 6, capacity 6, we have true. Now what about 7? Well, we are able to do it with 6. We should be able to do it with 7, right? There is no reason to even check because it's a bigger capacity, so we'll be able to do that. Now with 8, it will continue being true. So that's the idea of this function here, and you can see it's clearly monotonic. So that's what we'll use for our binary search. Now the question becomes, are we looking for the first true or the last false? Well, we are looking for the first case, right? For the first true, because we want to minimize the capacity, right? Let's say, for example, in this case, we don't want 8, we want 6. We want the minimum value of the capacity that will allow us to ship within D days, right? And so what we are looking for is the first true value, right? So we are looking for the first true value. In this case, it's 6, okay? Okay, so now with this idea in mind, we just need to figure out a couple of things. One is the initial value of low and the initial value of the high positions, and then we can apply just the template binary search. So the initial value of low, well, it just needs to be something that is guaranteed to be false initially, right? It's guaranteed that we were not able to ship packages within D days if we use that value. Well, in that case, we can just use 0, right? With 0, we can't ship anything, right? So we can use it because it's guaranteed to be false. The invariant here is that f of low needs to be false. Okay? And for high, we need f of high to be true. Okay? Those are the invariant for this binary search, so that we can maintain always low is false and high is true. And so for high, what's the value we can take? Well, we know that we certainly will be able to, if we take the sum of all the weights, right, we'll be able to do that within 1 day, right? And so let's just, if we take the sum plus 1, then we should largely be able to do it. So we guarantee that it's true. So let's just take the sum of the weights, then plus 1, so that we are guaranteed that that will happen. Okay, and then we can search on this range. Now the only thing is moving low and high. How do we do that? Well, let's say our mid is here and we find that it's true. Well, we need to put high here at the mid. You may say, why not put high at mid minus 1? Well, because maybe the mid that we actually found, because we only know that it's true, we don't know if it's the first true or it's the second true or the third true, right? So, but if it's here, we don't want to put a high here, because then we violate the invariant that f of high is equal to true. And so to make sure we keep that invariant, we are going to just always put high at mid, right? And similarly, let's say if mid was, if the function was false, which means basically mid was somewhere one of the false values, then we want to place low at exactly mid, right? We don't want to say that low needs to be at mid plus 1, because if we do that, then let's say our mid was actually here, then we'll end up with low here, and low will be true, and we will violate this condition, this invariant here, right? And so basically, this means that if f of mid is true, then we want high to be equal to mid. That's what we just saw. And otherwise, we want low to be equal to mid. And so this is really more straightforward, because you don't need to do plus 1 and think about whether you want to do plus 1 for low or for high, right? So it's a lot easier. And that's pretty much it. Now we have the structure of our binary search. The only thing remaining is that how do we calculate this f of x function? Well, that should be easy, right? Just what I did here, we just go through them, right? And accumulate the weights, and as soon as we reach capacity, we start a new day. So for example, here with capacity, let's say equal to 6, we'll just go here and say we have, so first 1 is still within the capacity, smaller than the capacity, so we add 2. It's still 3, still smaller than capacity, so we add 3, 6. But then when we try to add 4, it's 10, it's more than the capacity, so we need to start another day. So let's say, let's call them used days, right? So first we just used 1, and then when we find that we no longer have capacity, we add a new used day, so now it's 2, and the capacity is now 6. 6 minus 4, we have 2 remaining, right? And so we go to try to add 5, we can't because we only have 2 remaining, and so we increment the day, and now capacity is 6, and we do 5, remaining is 1, and we are done. And we find that as long as the number of used days, right, is smaller than or equal to the number of days, we should be good, right? We can't, for example, with the days are just 3, we can't use 4 days, right? So it has to be smaller for this function to return true. Okay, and that's roughly the idea of how we will implement the function itself. And then we do binary search. Now, what about the time complexity? Well, for our binary search, for each call, we will call this f of x function, and our f of x function, as you just saw, it goes through the entire array. So it's O of n, right? And binary search itself is we are doing it on the sum of the weights, right? And so it's roughly O of log of the weights, let's call it m, the sum of the weights, right? Because that's the search space, and then this is n because of the function f of x, right? So this is the time complexity. Now our weights can be up to 500, and so you can think about this is almost like still reasonable. It won't exceed 10 to the power of 4. It won't exceed the length of the weights, and so multiplied by 500, and so this should largely pass, right? Yeah, so that's pretty much it. Now let's implement this and make sure it passes. Okay, so let's implement what we just saw in the overview. So we need our f of x function, and then we need low and high. And as we said, we need 0 and the sum of the weights plus 1. One thing to note is that we deliberately choose these to be outside of the possible range of the solution, because we don't want to... In some cases, you might get a function that is all false, or you might get all true. And so if you are not careful and you put this in the range, you might not actually find a solution, right? And so that's just why we make sure we put low and high outside of the range. So this solution aims to minimize bugs as much as possible on your binary search implementation. And so that's why we are really careful here. And so we will go through, because we always want low to be false and high to be true, we arrive at the solution when the difference between both is just 1. And so that's what we do here. And then we calculate our mid position. And so this would be low plus high divided by 2. And then if the function returns true, let's call this function something better. Maybe can happen or something possible, let's call it, right? So if it's possible to ship within days here, using this capacity, then we want, this is true, so we want high to be mid. Otherwise, we want low to be mid. This is what we saw in the overview. And the answer is the true value, right? Because that's what we want. We want the minimum true value, and so we return high. Okay, so now we need to implement this function here. So this is the capacity we guessed as input. Let's call it x. So we have a capacity initially equal to x, and then we go through the weights. And then we want to keep track of the used days. So first we are at the first day. You need to be careful here. You shouldn't put 0 because it's not the 0th day, right? The first time we ship, it's the first day, right? And so here we want to say if the capacity is smaller than the weight, because it's bigger, we can't take it, right? But if it's smaller, we can. And so, sorry here, what I meant is if the weight is bigger than the capacity, then so this would be the remaining capacity we have. If the weight is bigger, that means we have to start a new day. And so we increment our used and we initialize our capacity to x, because we start a new day, and so the ship is empty, right? After that, we want to subtract the weight because we add this package to the ship. Now, if doing that makes it smaller than 0, even let's say after starting a new day, then that means, let's say, so this can happen, let's say if we have capacity of 2 and the list of weights has value 3, right? Then if you subtract here, even after starting a new day, the value would be negative. And so we want to say that that's not possible if that's the case. Now, otherwise, right, once we finish the weights, right, and then we finish the capacities, what we care about is if we were able to do that within D days, within the number of days we have. And so we just want to make sure that the number of days we used is smaller or equal to the number of days we have, right? So that's that. And that should be it. So now we have our function that returns true if it's possible. So if it's possible to, so it returns true if it's possible to ship packages in days within with capacity, ship capacity X. Okay, so that's roughly that's the core of this function here. Now if we run it, looks good. Let's submit. And that passes test cases. Now in terms of time, we said this is O of n because of this function here, n being the length of weights, and O of n log m, and being just the sum of the weights. And so that one should largely pass. In terms of space, we are using no extra lists really, so roughly of 1 space. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.